Okay, so now we move on to a new topic, which is called the fracture of cracked members. The key word here is fracture. And the question we are interested in is, well, ultimately, whether the material is brittle or ductile, the material in a tensile test experiment, for instance, ultimately breaks apart. And the question that we are going to ask is, why is this happening? What is the mechanism, underlying mechanism for this ultimate failure of the material? Why doesn't the material stretch forever like a gum? Why does it have to break apart? And we want to concentrate on a very basic mechanism that is responsible for this. Well, the extent to which it is responsible for the ultimate failure depends again on the material type and whether it's brittle or ductile. But if it's a brittle material, this is really the mechanism, one way or another, that is responsible for failure. Fracture is the mechanism. And we want to concentrate on the physics of fracture and the mechanics of fracture in a rather idealized setting with simple geometries, relatively simple geometries. A tensile test specimen is a relatively complicated geometry. We want to concentrate on simple geometries within which we can observe the mechanics of fracture. And with brittle materials, we know that there is little or no plasticity, so we will be concentrating on the analysis of fracture in a setting where plasticity is omitted. So we are going to look at linear elastic fracture mechanics. And this is usually abbreviated as LEFM. Now, I think the best place to start the discussion of fracture is to remember the concept of stress concentration. And we will remember this concept by taking a very fundamental problem of a plate with a hole in it. Okay. Now, the plate eventually is going to be subjected to some tensile loading, and the net load might be P, but load over area is going to be called, let's call it S. Often this is called the far field stress. It's called the far field stress because load over area, or the local stress field, the tensile, let's say the stress, normal stress in that direction, is not going to be uniform when we are rather close to the hole. But if we are sufficiently far from the hole, load over the normal stress in the vertical direction will be uniform, and that's why it's called far field. We need to be sufficiently far from the point position of the hole. Then there are the dimensions of the plate. That's T, the thickness. The half width of the plate is called B. This is a typical way to indicate the dimension. So let's try to get used to that. Of course, the plate is pulled in both directions. Then the radius of the hole, or the half width of the hole, is going to be called A. Now notice that I could have indicated the radius alternatively as rho. That's a typical way to indicate the radius, and the radius is A. Okay, so the half width of the hole is A, the radius is also A. Now, we want this, the upper surface to be sufficiently far from the position of the hole so that the stress field is uniform. So we are going to somehow enforce that through the condition that the height of the plate is sufficiently large compared to the half width. So in other words, the hole is relatively small in comparison to the height of this plate. Now, eventually, I will also impose the condition, and this is very important. I'm going to eventually also impose the condition that the hole is much, much smaller than the width of the plate as well. But we'll do that in a second. So what we would like to do at this point is, so what we have is a circular hole, right? What we would like to do is we would like to look at the stress field that forms at this cross section. So I'm just going to take a cut along the green line right through the center of the hole, and I'm going to try and depict the stress field. And from now on, unless otherwise necessary, I will go ahead and just draw two-dimensional pictures. So that is where I take the cut, that's the hole. Again, the height is much larger than the radius of the hole. That's an assumption. I am, for drawing purposes, not sticking to that assumption. So that is the stress that we are applying, okay? And the question is, that's the center of the hole, what is the normal stress at the cross section, okay? Well, what we can remember from ME 231 discussions is the concept of a stress concentration. Now, the stress concentration idea works in the following manner. So we have a hole, if you like, assume that it is sufficiently small such that if I am sufficiently far away from the location of the hole, the points here do not really feel the presence of the hole, so they think that the normal stress is the same as the stress that you encounter in further upper portions of the plate, which is S. So the points here are going to experience a normal stress that is the same as the normal stress a little bit further up on the plate. Okay, so the idea is that these points do not feel the presence of the hole, so they think that the plate is a perfect plate with no hole in it, and therefore the stress would be uniform. So because that's sort of an expectation, let us indicate the level of S with this red line. So that's where S is, and that's where my actual stress field is going to start from. But as I get closer to the presence of the location of the hole, the stress field will change because it will start to feel the presence of the hole. And what we also know is that the average stress throughout this cross section is certainly higher than S, because S times area should be equal to the average stress times the area of that cross section, and the area of the cross section here is less than the area here, right? So the average stress needs to be higher, and therefore the stress needs to change, and the way it will change is it has to increase so that the average stress is eventually higher than S. So points far from the hole do not feel the presence of the hole, so the stress is S, but if I get closer to the location of the hole, the stress will change, okay, and it will increase in this fashion, and that distribution is symmetric. And this is where we observe the maximum stress. Okay. Now, the maximum stress is calculated, remember, through the stress concentration factor. And the stress concentration factor is a quantity that does depend on the geometry of the hole. So KT is our typical notation. And what I'm going to do is I'm going to take a look at the ratio of A to B. It can vary from 0 to at most 1 when the hole fills the whole cross section. And we know that in that case, the stress concentration factor varies from all the way from 3 to roughly down to 2, and it will decrease in that fashion, okay, such that the maximum stress throughout the cross section is felt right next to the edge of the hole, and it is given as a factor, stress concentration factor, multiplying the average stress throughout the cross section. The average stress is, let's say, the net load on the cross section, which is S times this area, divided by the cross-sectional area where the hole is. And that cross-sectional area is the thickness times the width, which is 2b, minus the width of the hole, which is 2a. So that's the cross-section where the hole is present. Okay. So now the stress concentration factor, if A is large, then it's smaller. If A decreases, stress concentration factor will keep increasing, but the largest value you observe is 3. What's important in this case is now to go back and invoke that assumption when A is much less than B. When A is much less than B, B minus A is approximately equal to B, and therefore P divided by 2BT, so the load divided by the hole width times T should be equal to the far field stress. Okay. All right, so when A is much less than B. When A is much less than B, simultaneously the stress concentration factor takes a value of 3. Okay. So it turns out that under this assumption, the stress concentration causes a maximum stress that is equal to 3 times S. Okay. So now another thing we can look at is the we can look at a point, let's say here, and what I'd like to do is at that point I would like to indicate the normal stress. Okay, so for the case when A is much less than B. So what I will do is I will put a coordinate system, an X there and a Y there. So when X is 0, I'm right at the edge of the hole, and when Y is equal to 0, I'm at that point. Okay, so X equals 0, Y equals 0, I'm at the edge of the hole. When X is 0 and Y increases, I move along that direction. When Y is 0, X increases, I move away from the hole. So I'm going to keep Y equals 0, and I'm going to keep varying X, and I'm going to monitor the value of sigma Y. Okay, the value of sigma Y, which is monitored at the point of consideration. And that's going to be a separate plot. And what I will do is here, I will plot the value of, let's do that in green, I will plot the value of sigma Y divided by S, the far field stress. So that's like a non-dimensional measure of stress because I normalize it by the far field value. And I would like to have also a non-dimensional measure of the distance from the hole. A convenient way to do that would be to normalize it by the dimensions of the hole, because the dimensions are important. I'm going to normalize the position X by the radius of the hole, which is actually A. Okay, so I am at the point Y equals 0, okay, here, and I look at the value of sigma Y. Sigma Y acts in that direction, okay, and I look at its value when I move left and right, let's say on this green line. Okay, now, well, how do I draw that plot? Now take a minute to think about it, because the answer is in this picture, and I'm assuming A is much less than B, so the answer is in that picture with the stress concentration factor being equal to 3. In fact, the variation is already depicted here what we are saying here is there's a normal stress. That normal stress is actually equal to sigma y because it's on the plane with normal y. And sigma y starts from 3s and decays towards s. So it's going to start from a value of 3 when it is right at the edge of the hole, and it's going to decay towards a value of 1 when you move away from the hole. Okay. So the value of 3 is specific to the case when A is much, much less than B. In that case, the stress concentration factor is 3. Okay, let's also keep this picture in mind because eventually it is going to be useful for us just in a moment to think about how the stresses vary when we have a hole with a slightly different shape. All right, good. Now, on the side, you may wish to remember that the thickness is going to be a parameter that is largely irrelevant in most of the upcoming discussions because the thickness does not influence the stress concentration factor. So in a similar fashion, the thickness is going to be irrelevant in many of the parameters that we are going to be discussing shortly. Okay, so now this is just a review of what we already know from ME 231. So now what I would like to do is I would like to consider a hole with a different shape, and it's going to be an elliptical hole. Okay, so again we have a plate. And there's going to be a hole, but that hole now is not circular, but rather elliptical. Let's say like this. The half width, again, is going to be denoted by B. The half width of the hole is also going to be denoted again by A. Now, there is again the thickness of the plate, which is T, and I'm going to apply again a far field stress S. From now on, for a certain while at least, I'm always going to assume that the half width is much, much less than B. And it also goes without saying in almost all of the discussions that the height of the plate is going to be much, much larger than the width of the plate, so that this picture is meaningful, so that the stress distribution, normal stress distribution here is uniform. So that's the geometry of the plate. Now I'm going to introduce two more dimensions. So because it's elliptical, it's not sufficient to just define the half width. I need to also define the height of the ellipse, and let's call that D. But more useful eventually is going to be a slightly different quantity, which is the tip radius. Now, along any curve, suppose you have a curve like this, okay? You might remember the concept of radius of curvature from ME 231. So whenever you have a curve, and if you concentrate at a certain point, let's say that point, there is always going to be a circle that locally reproduces the geometry of this curved line to the best possible extent. So what does that mean? Well, I will try to fit a hole, fit a circle that's going to somehow fit to this line locally very well. If I draw a very large circle, it won't be a good approximation. If I draw a very small circle, it also won't be a very good approximation. But if I draw a circle that, let's say, looks like this, you see, it's a circle that is able to locally fit to this blue curve quite well. Okay, so this concept has to do with the radius of curvature of this blue line at the point that I am considering. Okay, and that radius has to do with the radius of that circle. So similarly, there is the radius of the best circle that I can locally fit to the tip of this ellipse. And that circle, let me depict it like this. Okay, and that circle is just a geometrical virtual shape that I'm drawing. There's only one hole here, and that's the elliptical one, but I'm trying to fit a circle to the tip of the ellipse, and that circle, let's say, has a radius rho. Okay, now it turns out that that radius rho can be calculated in terms of the major and minor radii of the ellipse, and it is given as d squared over a. Okay, so, and that is called the tip radius. All right, now we have the full geometry of the plate. And now what I would like to do is I would like to concentrate again at a certain point, at this point on the hole, and I will monitor the stresses as I move along that direction, which is called x. Of course, x cannot exceed the edge of the plate, but it's just to show the direction. And this direction is going to be called the y direction. Okay, and what I will do is I will again take a element that is located at the along the y equals 0 or along the x-axis, such an element. And such an element will have normal stresses along the y as well as along the x direction. And what I will do now is I will try to depict the variation of the normal stresses as I move along the x-axis. So I'm moving along the x-axis. I will, just like we did here, I will normalize that dimension by the tip radius, in this case, of the ellipse, because that's, it turns out, a convenient quantity. And what I am monitoring is the normal stress. It's either going to be x or y, and I'm going to, just like I did there, normalize it by s. Okay? Now, you will remember that in this case, we will also have a quantity that is essentially the stress concentration factor that's going to give rise to larger stresses in the vicinity of the hole at x equals 0 or x over rho equals 0, and smaller stresses when I move away from the hole. Now, but we have to be careful about the stress component to which that discussion applies. So remember, what we are doing here is this is the hole, and the shade indicates the rest of the plate, and I am locally moving in that direction. So that's x, and that's the y direction. And what I am doing is I'm looking at an element that is located here, and that element at a certain point x and at y equals 0, right? Y equals 0 is what we're considering. There is a sigma x and there is a sigma y on that element. Now, let's first look at the value of sigma y. Well, again, we have the stress concentration concept. What we expect is that when we are very close to the presence of the hole, then the normal stress in the y direction, it's going to be high. But if I move away from the hole, the normal stress will decay to a value of eventually 1 when I'm sufficiently far from the hole. Why? Because the normal stress, if I'm sufficiently far from the hole, the point here does not feel the presence of the hole, it turns out, so it will think that the normal stress sigma y, which is in that direction, is essentially the same as s, because it will feel as if the plate is a plate with no hole. Okay, so because the normal stress is s, then sigma over s is going to go to 1. So this is the curve that is associated with sigma y over s. So it turns out that the sigma y max that we can measure in this case is, as you will remember, again, a stress concentration factor times the average stress on the cross section. But because we are assuming A is much, much less than B, the average stress on that cross section is approximately equal to S, just like we argued over there. So that's the average stress, and what's going to go here is the stress concentration factor, and that stress concentration factor is 1 plus 2A over D, which is what you might remember from your mechanics on materials course part 1. Okay, and what we can also do at this stage, I think it's useful, is to replace this expression so that rho appears in the expression, and by isolating D as A times rho square root from the definition of the tip radius, what you can do is you can write the stress concentration factor as 2 square root A over rho. Okay. So that's our stress concentration factor for a elliptical hole when A is much, much less than B. Okay, now we're going to come back to this stress concentration factor in a second, but before we do that, let me draw here what the value of sigma x is, or how it qualitatively varies, because it's going to help us, again, qualitatively in our next discussion. Now, it turns out that sigma x is a strange, or has a strange variation. Now, first of all, we can think about the value of sigma x at two extreme points. So at that point, sigma x is the normal stress on the plane with normal x, right, in the direction x, which is that direction. Now, let me ask you a question. What is, therefore, sigma x at that point? Okay, so we have a plate, it's a hole, and the only load that I'm applying on that plate is exactly where, exactly on the upper and lower surfaces, right? Again, goes without saying there's a stress applied on the lower surface as well, but nothing applied within the hole, right? So what is sigma x on the plane with normal x in the direction x? Okay. Well, the answer is, well, there's nothing applied. It's a free surface. Remember, that's a concept that we have employed earlier. Because it's a free surface, sigma x at this point is going to be 0. So it's certainly going to start from 0. Well, what is sigma x when I'm very far away from the hole? Well, if I'm right at the edge of the plate, again, it's a free surface, so it should start from 0 and it should go to 0. But we could do a small free body diagram analysis and really ultimately conclude just from a qualitative discussion that actually sigma x cannot be 0 in between. And it turns out that sigma x indeed is not 0. It becomes, interestingly, positive somewhere in between. And then we know it has to decay to 0, so it will decay to 0. Okay, so that's the variation of sigma x over s. So despite the fact that I am only pulling along the y direction, the presence of the hole immediately induces a state of multi-axial stress in the vicinity of the hole. Okay, despite again the fact that I'm only pulling in one direction. Okay, good. So this multi-axial state of stress is just as a qualitative appearance is going to help us understand in a second what's going to come up. Now, let's look at this stress concentration factor. The stress concentration factor is, it turns out, a function of the dimensions of the hole. Now, what I can do is I can keep the half width of the hole constant, and that's A. So A does not change, but I'm going to keep the tip radius, so A is a constant, the tip radius, and for that matter, the vertical width of the elliptical hole, a variable. Okay, so if I make the width smaller, D will decrease and therefore rho will decrease. A is constant and is much less than B. What happens in that case to the stress concentration factor, right? Well, what happens is that so I'm going to let D over A decrease, in fact, towards 0. So it's getting thinner and thinner. So this is the way the plate looks with a certain value of D, and this is the way it looks for the same half width with a smaller value of D. So here D1 is greater than the value of D2. And if D becomes even smaller, in fact, if it is almost 0, what I see is almost like a slit. Okay, D over A goes to 0. And in that case, because D is going to 0, the tip radius is going to 0, and the stress concentration factor will blow up. If the stress concentration factor blows up, what we observe is, as a result, sigma y max goes to infinity. Okay? Now, that is an observation that is important consequences, because I am looking at a material that is governed by linear elasticity. So I'm assuming essentially brittle, right, materials. And brittle materials eventually have some ultimate strength. This stress, right, provided the tip radius of the crack is sufficiently small, ultimately there will be a point, let's say right at the tip of the elliptical hole, there will be a point where the stress is sufficiently large so that it will exceed the ultimate strength of the brittle material, and locally the material certainly will fail, right? So that's something we need to keep in mind. So what this analysis is saying us is that if we put an elliptical hole in a plate and we pull on it in the manner that we've described, and we make the hole thinner and thinner and thinner, ultimately the stresses will be so high that the material will try to break apart. And that is sort of the motivation for what we are going to go ahead and analyze. Now, in this scenario, the way I'm going to depict the geometry of the plate is simply through a picture where I will draw a plate of width 2b, which has a crack of width 2a. Okay, so from now on, this is what I'm going to assume, that the tip radius is very small, such that we have an ideal slit or a crack-like geometry of the elliptical hole. So that's our definition of a crack. And instead of drawing the picture like this, I'm going to just go ahead and draw the picture as such. Okay, so that's our now point of departure for the upcoming analysis.